Chapter 8 is all about electricity and magnetism. Electricity is the flow or movement of electrons along a substance. So what are electrons? So looking back at our chemistry chapters, electrons were those subatomic particles in an atom that surround the nucleus of an atom. So they are negatively charged particles. These electrons is what makes up electricity. And if you remember looking at the electrons, the properties of the electrons, they have a -1 charge and their relative mass is pretty much zero. They're so small that their mass is negligible. Electricity is the movement of the outer shell electrons only. So when we talked about an atom, we talked about the nucleus being the center with the protons and the neutrons, and the electrons on different levels surrounding that nucleus, orbiting around it. So the outer shell electrons, the electrons on the very, very outer shell, those are the electrons that are available for electricity. We're going to focus in this chapter talking about static electricity. So back in ancient Greece, they discovered static electricity when they were polishing an amber stone. And what they realized when they polished this amber stone was that it enabled the stone to pick up pieces of straw. It did this because of the static electricity that was created with the friction of polishing that amber. So the word electric is derived from the Greek word for amber, which is electron. So what exactly causes static electricity? Well, static electricity is due to electrons actually being rubbed off from one substance to another. Because whenever we see static electricity, it's always from two objects that have rubbed together. And what's happening with that friction is that electrons are being transferred from one object to the other. So this transfer of those negatively charged electrons is causing one object to be negatively charged, while the other object is positively charged. So think of the example shown in this picture here. If you've ever taken a balloon and rubbed it in your hair and then pulled that balloon away from your hair, what happens is you see your hair follow the balloon. And the reason for this is because while you're rubbing that balloon on your hair, you are rubbing off electrons from your head to the balloon. This causes the balloon to be negatively charged and your hair then to be positively charged. And we know that opposites attract. Positive and negative are opposites, so they're going to be attracted to one another, and that is why your hair is attracted and follows the balloon. Another good example of static electricity, I don't know if you've ever done this when you were younger, but I had older siblings. We would have socks on the carpet, and you would rub your feet on the carpet, trying to build up some static electricity through that friction. What you were doing is you were actually rubbing electrons off onto your feet. Then you could go and touch the other person, and you would shock them. And what that shock feeling is, it's actually an electron jumping from your finger to the other person. If it's dark in the room and you do that, you'll actually see a small spark. Another example of this is if you've ever dried blankets in the dryer, right? The blankets are in there, they're tumbling around, they're creating friction, they're going to get some static electricity. If you shake that blanket out, you can actually hear the sizzle of that static electricity, of those electrons jumping. Opposite charges attract and like repel, so this is why in all of those examples you have a negative and a positive charge being attracted to each other. So now we're going to look at how conduction and electricity are related. So what adduction is a process in which a charged object is brought near but not touching a neutral object, and in the presence of that charged object, the neutral object will become charged. Okay, so that sounds a little bit confusing. So let me explain it a little bit better using this example here. We have a plastic rod with a charge on it. So you can see this orange plastic rod, and it has these little negative signs around it indicating that it is negatively charged. Okay, well, if we bring that negatively charged plastic rod near a neutral object, what's going to happen, because of the fact that opposites attract, is that those negative charges are going to attract the positive charges, causing the positive charges to come to the surface. And what this does is it pushes all the electrons, all the negative charges away, since like charges repel. So this induces a positive charge on that object. So let's look at another example. So in this example, we have a positively charged glass rod. So the glass rod over here, notice, has all positive charges. So if we bring that near a neutral sphere, and by neutral I mean the same number of positive and negative charges, what's going to happen in this case is that opposites are going to attract. Those positive charges on that glass rod are going to attract the negative charges of the sphere, causing them to all come near the surface where that positively charged glass rod is, pushing the positive charges as far away as possible. So this positively charged glass rod is inducing, through induction, a negative charge on the sphere. It's called induction because the two objects become close, but they do not touch. If they were to touch, it would be called conduction, like we looked at in Chapter 7. Let's see how static electricity and induction relate to each other. So induction, we just defined that as the ability for a charged object to induce a charge on a neutral object. So in this little experiment that we have here, and you can even do this at home if you get bored, take a balloon, rub it on some clothing or on a blanket or something to get some static electricity going. And by doing that, by creating that static electricity, what you're doing is you are creating a negative charge on the balloon. So looking at this diagram to the right, the balloon has a negative charge, so that's similar to our charged objects. Now, if you bring that charged object, that charged balloon, near a small stream of water from your faucet, well, that small stream of water from your faucet is neutral. What that means is it has the same amount of positive and negative charges in it. So by bringing that negative balloon towards that neutral stream of water, you're going to induce the opposite charge. In this case, you're going to induce a positive charge. Well, since opposites attract, what's going to happen is that stream of water is going to come follow your balloon as you pull the balloon away, because you have a negatively charged balloon and you have now induced a positive charge on the water. So by moving the negatively charged balloon away, that positively charged stream of water is going to curve towards the balloon and follow it. So now let's relate static electricity to lightning and storms. So who discovered the relationship between static electricity and lightning was Benjamin Franklin, by doing an experiment you may have heard of where he flew a kite during a storm. And how he set up this experiment was that he had the kite tied to a string. And then he had a key tied near the end of the string, which you can see in this diagram here. On that key, he also tied a piece of silk string. Okay, so the key's purpose was acting sort of like a conductor. And what happened while he was flying this kite in the storm is that the kite picked up this ambient electrical charge that comes from storms. And he noticed that the string tied around the key, that silk string, started to rise a little bit, kind of stick out. So what he did is he reached up his hand and got it not touching but near the kite and saw that little spark that we talked about jumping from the key to his finger. And this proved to him that storms were made up of electricity, of electrons, because that spark that he saw was really just electrons jumping from the key to his finger. So lightning is actually just static electricity on a much, much larger scale. So what happens during thunderstorms, it gets cloudy out. And since there are so many clouds, those clouds are creating friction by rubbing against each other. So when they get that friction, static electricity occurs and you get a separation of charge. You get negative and positive. So looking at this picture here, electrons are rubbed off from one cloud to another. So you have one cloud with a negative and one cloud with a partially positive charge. So when those clouds get close to Earth, because they get lower and they get closer to Earth, they induce a charge on the Earth. So this is where induction comes into play. So the ground that we're walking on is neutrally charged overall, for the most part. It's the same amount of positives and negatives together. So this neutrally charged Earth, when those negatively charged clouds come close but not touching, they induce the opposite charge. Whenever you have a negative and a positive in close proximity to each other, you have the possibility for electrons to jump that gap, much like when that spark jumped from the key to Benjamin Franklin's finger. He didn't touch the key, he just got it close. So those negatively charged electrons jumped, and those jumping in the form of lightning, so much larger scale. It's also why you can see sky lightning often. You get two clouds that come near each other. They induce opposite charges on each other, and you get these electrons jumping from the negatively charged to the induced positively charged cloud. Benjamin Franklin also used this theory with static electricity and storms to create lightning rods. His initial purpose to create lightning rods was he wanted to try to trap the electricity from storms so that we could use it on a daily basis. That unfortunately didn't work, but the lightning rod idea was helpful in other areas. He used lightning rods to help direct the electricity from storms away from a house. So if you had a lightning rod on your house, that lightning rod would be connected to a wire that would run alongside your house, and then a grounding rod. This grounding rod would allow that electricity from that storm to go into the ground instead of damaging the house, protecting it from lightning strikes. Some practical everyday uses that we might see for static electricity, one of them would be air purifiers. So if you have an air purifier in your house or know someone that does, I'm going to kind of explain how some of them work. So with an air purifier, you get dirty air going in, so it's going in these blue arrows in the bottom. Now that air is first going to go through a mesh filter, which just filters out the larger particles. Well, not all particles will be caught by that mesh filter. So it continues on and goes through a positively charged grid. What that does is it makes all particles that are traveling through that grid have a positive charge. Then they next go up through this red filter, which is the negative grid. So what happens when a positive and negative get near each other? They attract. So those positively charged particles are going to get stuck in the negatively charged grid. Then of course, just for good measure, some of them even have a charcoal grid at the end to get any particles that maybe weren't trapped through that initial positive-negative attraction. So a quick review on static electricity. Remember that opposite charges attract, so positive and negatives attract. Like charges therefore repel, so they want to get away from each other. Positive and negative charges attract neutral objects through induced charge. So there's a picture of that off to the right on the bottom here. So we have a positively charged sphere in this case coming near a neutral sphere, sphere B, causing it to have a negative charge because of that opposite attraction thing. And with induction, remember that the charged object, in this case A, comes close but not touching the neutral object. That's how the charge is induced. And then also forces between charges decrease with increased distance. So all that means is if I had two charged objects and they were really far apart, the attractive force between them wouldn't be strong. However, the closer I would bring them, the stronger those attractions would be. Think of magnets, which is what we're going to talk about next. If you have two magnets, a north and a south pole, and they're near each other, you can actually feel them pull towards each other. You can feel the forces. The further apart they are, the less you feel those attractive and repulsive forces. So since we were talking about magnetism, let's see how magnetism and electricity are related. So first, let's start by the definition of magnetism. It is a physical phenomenon produced by the motion of electric charge. So this also has attractive and repulsive forces between objects. The earliest magnets were found to be the mineral magnetite or lodestone. So there's pictures off to the right there of both of those minerals. And what they're made of is an iron ore material. And they have a natural magnetic property. They were actually used as a compass to guide early sailing vessels, since they did have those magnetic properties and could point in a specific direction due to that. Some properties of magnets. So they have attractive and repulsive forces as well, much like electricity, electrons, the positive and negative forces. But they're called something different. Instead of positive and negative, we have north and south poles. So we still have opposites attracting. So north is attracted to south and south is attracted to north. And likes are still repelling. So if we have a north and a north end, they would push away from each other, and same with south and south. Continuing on with properties of magnets, how does a compass work? Because a compass is really just a magnet. So the Earth is actually like a giant magnet due to its nickel iron core. So basically, inside the center of Earth, you can almost think of there just being a giant magnet in there with a south end and a north end, just like the other magnets we've looked at so far. And the compass works because the north pole of the magnetic bar in the compass, so looking at this picture here, the north pole of the magnetic bar is attracted to the magnetic south pole. Now the confusing part about this is that Earth's magnetic south pole is its geographical north pole. So electricity and magnetism can work together. Both have similar properties. They both attract or repel. So likes repelling, opposites attracting. Electricity does this with positive and negative charges, and magnets do it with north and south poles. Now when you combine the two and you get an electric current passing through a wire, you can actually form a magnetic field, creating what is called an electromagnet. So that's what this picture up top is kind of showing. The red arrows are the electric current. The pink circles are showing the magnetic field that is formed due to that electric current running through that conducting wire. So let's look at a simple electromagnet and how that works. So you need an electric current passing through a coil. So what I have a picture of over here is one that I wish I could have shown you in class, but we aren't having average classes, but this is copper wire in yellow here that I'm redrawing in red. It is attached to a voltage source, or a battery in this case. And you take this copper wire and you can wrap it around an iron nail. And when you connect the ends of this circuit, letting the voltage and the current run through, by having that current run through, you're making this iron nail now magnetic. So the iron nail, which couldn't have picked up any other nails alone, now that it has that current running around it, it is magnetic, and it can now act as a magnet and pick up other nails. Now this is a simple electromagnet, so it's not going to be very strong because it's just powered by a battery. But you can increase the strength of an electromagnet by doing a few things. One of those is the number of turns of coils. So what I mean by that is going back to the example of that copper wire. If we would have wrapped that copper wire more times around the iron nail, we could make that magnet stronger. So more coils would increase. The other thing, the amount of current. So bigger battery, right, to create a larger current. So looking at a larger scale with electromagnets, we have a crane that can actually lift vehicles with how strong it is. Electromagnets are also used in motors, and you probably heard of MRI machines, which are magnetic resonance imaging, which also has some of this theory supporting its function. So for electricity and electric current, electricity is generated whenever a charge is moving. So in this picture here, these little Q's with these blue spheres, that's our charge moving. So when that charge moves, electricity is generated. And the electric current that we've been talking about is just the flow of that charge, so that charge moving. It's determined by how many, or the quantity of charge that passes through an area at any given time. And we're going to look at some ways to calculate current, mainly using Ohm's law. So electric current is the flow of moving electrons along a conducting wire. Copper is an excellent conductor of electricity. I used it in the example of the electromagnet a moment before. A lot of houses also use copper wiring in them as well. It is a little more expensive now than it was when it originally started to be used as a good conductor for wires, but it's still readily available and abundant. It's a transition metal, so if you remember back in the chemistry chapters when we talked about transition metals, it has 11 electrons in its outer shell, and remember, only those outer shell, those valence electrons, are available for electricity, so the more the better. It's ductile, which means you can bend it repeatedly without cracking it. And oftentimes, when we use any type of conducting wire, we need insulating substances to prevent overheating or any shortage. Now let's bring this idea of electric current to an electrical circuit. So an electrical circuit, we're going to have a current running through a conducting wire, and that's the arrows in red in this diagram over here. But to have a complete circuit, we need more than just current, which is the amount of electricity going through. We also need a voltage. Okay, and the voltage is going to be the speed of the current. So in this case, this battery here in blue. But also, what's the point of an electric circuit? Well, it's to get something to work, right? You want to turn a light bulb on, or charge your phone, or plug in a clock. So that part of it is called the resistance. So this is the measure of the degree which a conductor opposes an electric current. So it's taking part of that current to light up that light bulb. So it is being a resistor in this circuit. So to calculate any of these three variables that we just talked about, we're going to be using what we call Ohm's law. So in order to have a complete circuit, we need voltage, current, and a resistor. So that's where this equation comes from. V is equal to IR. V is the voltage from the battery source. It's measured in volts, so that's kind of an easy one to remember. The I in the equation is current. So that is the charge moving through the wire. And it is measured in amperes or amps, so capital A for those units. Resistance, R, so the light bulb, clock, whatever is attached to the circuit, is measured in ohms with this funky looking symbol here. So all of these units are written on your equation sheet along with the variables so that you can remember which is which. So notice in this circuit we have over here, we have the voltage at the battery, the current running through the wire, and then the resistor would be the battery, and it's got a 1 ohm resistance right there. So let's talk a little bit more about resistance and what these resistors are. So when an electron is traveling through the wires, it will encounter a resistance or a resistor, and that would be whatever you have plugged into the circuit, whatever you're trying to charge, light up, etc. So this resistor is a hindrance to the flow of charge because it's using up some of that charge. This flow of charge, when encountering resistors, is often compared to water in pipes. And the resistance then would be when there's a clog or any friction in the pipe, because you need that water to go around the clog. So it's going to kind of slow it down. Resistors do the same thing. When that electrical charge, that flow, encounters a resistor, it might slow it down. It's got to go through that obstacle to continue moving on. So let's look at circuits with multiple resistors. So there's two different types of resistors we're going to look at in this course. One is called series and the other is called parallel. So for a series configuration, we have one following another. So they're just right in a row. So you have the current flowing through one resistor, being the light bulb, and then once it's through that resistor, it goes through the next, and then the next, and then continuing on its path. With parallel, it's different because when you have the current flowing, once it reaches this first light bulb, it's going to split. So some of the current's going to go into that light bulb, and then the rest of the current's going to continue moving forward until it hits the next light bulb. It is then going to split again. Part of it going through the second light bulb, and then the rest continuing through the final. So for parallel configurations, the current is not the same through each resistor. And we'll look at the comparisons of both series and parallel here in a minute. Wanted to look at the series resistor a little bit closer. So we have the batteries, which is the source and the destination of the electrical current, right? We need to be connected to both ends of the battery for the current to flow. The same current is flowing through all three light bulbs because the current's going to flow through one, and then it's going to continue and flow through the next, and then the next. So it's the same current through all three resistors. Over to the far right here, we have a drawing of generally how we draw these resistors. So this R1 would be light bulb 1. R2 would be the second light bulb in the diagram, and then R3 would be the third light bulb. So these resistors are represented by these little squiggly lines here. And then we have the battery, as you can see, with its positive and negative shown here. When we're calculating the overall resistance or the total resistance for a series circuit, we are just simply adding those resistances together. So the reason we have R total is equal to R1 plus R2 and then dot 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 is because it depends how many resistors we have in that specific circuit. If we have 5, then it would be R1 all the way through R5. And I show an example calculation on the worked examples video following this chapter 8 PowerPoint. So for parallel configurations, it's a little bit different to calculate the total resistance because that current is splitting and going two different ways. So when we're looking at calculating the total resistance for parallel, we still have, in this case, 3 light bulbs, so an R1, an R2, and an R3, but to calculate it, we're going to be calculating 1 over R total. So when we're done doing this calculation, we need to do the inverse to figure out what R total is going to be. And once again, I show an example of this on the video. Remember that with parallel, each bulb has a separate current because of that current splitting when it gets to each in junction. So it's not the same current going through each bulb like it is for the series circuit, which have one after another. So here is a comparison of what you need to know between series circuit and parallel circuit. So for series, we said the current, that I value, is the same because it's the same current going through all 3 resistors. There's no splitting of it as it goes around. The voltage, however, is additive. Resistance is also additive, as we saw when we were looking at calculating R total. We just took the R1 plus R2 plus R3. But due to this, the brightness of the bulbs is going to be less as more resistors are added. So since the voltage is additive, every time you add another resistor into a series circuit, you're dimming the other resistors in that circuit because they're not getting as much. looking over at parallel. For parallel, since that current splits every time it hits a resistor, it's additive. It has different pathways, right? So the current's going, it splits. So we have different current going through each resistor. The voltage, however, due to that current splitting, is going to be the same. So you can add 10 light bulbs on a parallel and you're not going to see any of them dim because the voltage is going to be the same. The resistance we saw was 1 divided by the sum of the reciprocals. Okay, so that's that 1 over R total that we looked at on the previous slide. In comparison, parallel circuits tend to be brighter in comparing like light bulbs, for instance, than series circuits due to the fact that their voltage is the same and not additive. So let's look at some other pros and cons between series and parallel. So since it's the same current flowing through all 3 resistors in a series, it's drawing less current, so it's going to be cheaper. So that's a plus with series. A drawback, however, is that if any of the bulbs go out, then the whole circuit's going to be dead. So think of Christmas lights. Now they have better Christmas lights, not better, but ones that are on parallel circuits now. They used to have them series, where if one light bulb went out, your whole string would go out. And that's because it was a series circuit. If you took out one of those resistors, the current couldn't flow anymore because it's the same current flowing through all light bulbs. So it would stop flowing through that entire circuit. For parallel, each bulb has separate currents. So this is going to be more expensive, less energy efficient. However, if one bulb dies, the others remain on. And you've probably seen this with light fixtures in your house, whether it's over the kitchen table or otherwise. You have one light bulb go out, but the other ones remain on. That's because they're in parallel and the current doesn't stop going through the others because they have separate currents. So here are a few of the calculations that we're going to be going over in the video for the Chapter 8. So take a look at those. We're calculating using Ohm's law. We're also doing total resistance for series and parallel circuits. We have a few more equations to look at before the end of this chapter. And the first equation we're going to look at is relating power and electrical energy. So when we looked at power, I think it was back in Chapter 6, we said power was equal to energy over time. So since energy is the focus of this chapter, we simply rearrange this equation, and the equation we're going to be looking at is where energy is equal to power times time. When we're using this equation, we're using the same units we did in Chapter 6. So energy is measured in joules, capital J. Power we want in watts with a capital W. And then time we want in seconds. When we're looking at this energy equation, we're talking about electrical energy. So we've looked at kinetic, potential, work energy, heat energy. Okay, this equation is applying to electrical energy. So with electrical energy, let's look at what electrical power would look like. So if we wanted to calculate electrical power, you hear people say, oh, power went out. Okay, they're talking about electrical power. Each device has its own power consumption. So we can calculate that by multiplying voltage times the current. So voltage, once again, is going to be in volts. Current is represented by this letter I and is measured in amps. And then power is in watts. We'll look at a few examples with these calculations.